Good morning. I'm not Daniel Spielman. I'm sorry. I'm David Nurnberg, the director of the Institute, and it's my duty, my privilege, even my joy to introduce or to welcome you all to Visions of Arithmetic and Beyond, celebrating Peter Sarnak's work and impact. So given the fantastic breadth of Peter's contributions to mathematics, as well as the astonishing number of mathematicians he's worked with or influenced, it was evident that a multi-day conference was needed to celebrate his career thus far. And given his own work on primes, the number of days needed to fall somewhere between 3 and 2 to the 82,589,933rd power minus 1, assuming no further progress from the great internet Mersenne prime search. That the organizers landed on 5 is, I'm sure, entirely because of practical constraints, not because that in any way exhausts our appreciation of Peter's work. So I don't know if mathematicians are as fond of the Greek poet Archilochus's dictum that, quote, "A fox knows many things, but a hedgehog knows one big thing," which was turned into a classification of thinkers by Isaiah Berlin in his famous essay, The Hedgehog and the Fox. I was at first approximation about to categorize Peter as a mathematical fox, in that his interests are extremely broad, his work touching on many diverse fields normally plowed separately. As the Shaw Prize citation put it last week or so, his original and deep vision has launched a vast research program that brings together number theory, combinatorics, analysis, dynamics, geometry, and spectral theory. Now, that list is scarcely exhaustive, and I should add that many different aspects of his work have been prized, beginning with the George Porlia Prize from the Society for Industrial and Applied Mathematics in 1998, and concluding for now with last month's Shaw Prize, and I'm not going to pause to list the many in between. But just as in geometry, what requires a reflection in any dimension can often be done by a rotation in one dimension higher. If we view Peter from a slightly higher dimension, he looks like a hedgehog, one whose one idea, but he does. whose one idea is a strong sense of the unity of mathematics. In this sense, he is like his doctoral advisor, Paul Cohen, still the only person to win the Fields Medal for work in mathematical logic, a mathematician with unusually broad, and another mathematician with unusually broad interests. And that actually raises the question relevant to this room, whether in the case of students and teachers of mathematics, like attracts like, or whether an advisor's horizons shape those of the advised, but that's for a biographical session later. In any case, when it comes to mathematics, we can say that Peter is both hedgehog and fox, a mixture that the Greeks would have called monstrous. Peter is indeed a mathematical monster, and this monstrosity has been one of his great gifts to the discipline and to the Institute. The shape of the School of Mathematics as we have it today, and I presume to say that it is in excellent shape, owes a great deal to the breadth of mathematical taste and the generosity of judgment with which he and his colleagues have filled it in the past decades. For that, too, all of us at the Institute, and I dare say in the field of mathematics, owe him enormous gratitude. Peter is like Paul, so many apostles in mathematics. Peter is like Paul in yet another way. Both spent abundant time at the Institute for Advanced Study. Paul Cohen as a member from 1959 to 61, and again in 1967, and Peter for parts of 1999, 2000, 2002, 2005, 2006, 2007, and finally throwing in the towel, becoming a faculty member that year. My temptation as a historian was to head to the archives to find the members' reports that Peter submitted in those early years so they might chart the development of his work here and his evolving relationship with the Institute. But even without research, it's easy enough to discern his tremendous influence on mathematics, on his students, and on all the organizations where he has pursued his thought and teaching, especially Princeton and the Institute. The presence of many of you here is sufficient testimony to his teaching, for which I know he received the Phi Beta Kappa award, a teaching award from Princeton. If I may quote, and I hope I'm not embarrassing, Akshay Venkatesh's description of his studies with Peter, quote, "You would go in to see him, and of course you'd be depressed because you hadn't been able to do anything. But you'd come out of his office feeling cheerful. You'd come out feeling you're working on the right thing. That was really valuable to me. For a graduate student, it can be very difficult. It's very easy to get discouraged if you have no real understanding that you're going to be stuck for a very long time." So directors of institutes for advanced study also get stuck for long times, and I can attest that Peter has exactly the same cheering and illuminating effect on me. But I'll conclude with a less celebrated but tremendously fruitful aspect of Peter's many gifts, his talent for joint citizenship. He's not content with one citizenship when he can have two. And although I can't speak for the relative weight of his multiple nationalities, I can say that when it comes to his intellectual communities, Princeton University and the Institute for Advanced Study, he contributes to each as if it were his only care. Or rather, here too, if we just go up one dimension, he discovers unity in diversity, making connections that raise both institutions to a higher level. I know that many of you will have much to add to the admiration and gratitude I've tried to express in very brief compass. I didn't want anyone to faint at my taking half an hour at the beginning. And I've tried to express that admiration and thanks on behalf of all of us. So let me thank you all for coming. I'd also like to take this opportunity to thank the organizers, Alex Gambourd, Nick Katz, Hio, Kanan Sundararajan, and Akshay Venkatesh, as well as my co-sponsors, the Clay Mathematics Institute, the American Institute of Mathematics, the National Science Foundation, and Princeton University, and above all, the staff of the Institute for Advanced Study, who are so warmly hosting us today for making this celebration of Peter possible. And now I welcome my colleague Akshay Venkatesh.
Hello, everybody. I'm Akshay Venkatesh, and I would like to welcome you all on behalf of the organizing committee. We often see this hall filled for musical concerts. I think it's a bit rare to see it filled for what we have today, which is a mathematical concert. And I think that testifies to Peter's influence on mathematics and on many of us personally. I also want to welcome everyone who's here on Zoom. So unfortunately, the physical capacity of this room limited, was not equal to the number of people who wanted to be here. But for everyone on Zoom, welcome also, and I hope you can enjoy the talks remotely. I have just a few practical comments. There will be tea in the morning and afternoon breaks. So this is for the first 2 days, which are at IAS. There'll be different practicalities at Princeton University. So today and tomorrow morning and afternoon breaks will be in Rubenstein Commons, which is, you go out here and turn to the right. It's not the building directly in front of you, but the one behind it. There will be people to direct you. And the lunch will be in the dining hall, which is at the other end of campus. Again, there'll be people to direct you. There will be a reception tonight, a conference reception at 5:30, also in the Rubenstein Commons. If you are not registered, please go and talk to the staff. Okay, as I said, we're very close to the physical capacity of this room, so we need to keep track of numbers. Okay, so if you're not registered, just go and talk to our staff who are outside. And I think the only other thing I want to do is thank everyone who has made this possible. So I'd like to thank the Clay Mathematics Institute, the American Institute of Mathematics, and the National Science Foundation, all of whom have sponsored this conference, as well as IAS and Princeton University. And again, I would like to repeat what David said. I would like to thank the staff who have been working for many weeks to make this thing possible, and I hope you all appreciate the result. Thank you.
Morning. Ramanujan Graphs, written jointly with Ralph Phillips and Alex Lubotsky, is Peter's most cited paper, so I think it's fitting to start the conference with a talk on the impacts of Ramanujan Graphs, and I'm delighted to introduce the first speaker, Professor Daniel Spielman from Yale University.
Thank you. So I thought the best way I could honor Peter would be to not talk very much about my work, but to tell you about some of the impacts of his work, namely this famous paper on the introduction of Ramanujan graphs. So to summarize, what are Ramanujan graphs? Spectrally speaking, from an asymptotic viewpoint, they're the best possible expander graphs we can make. And I'd like to begin this talk with an introduction where I will explain exactly what that means. Then I'll tell you some about applications of expanders and Ramanujans and tell you some more about their impacts. To figure out how fast I should go and how much I should cover, I'd like to begin just getting a show of hands. How many of you are familiar with expander graphs? Many, but not enough for me to skip it. Okay. So let's start with that. I've drawn a picture of an expander roughly here. Okay, so first when we think about expanders, you think about a family of graphs of fixed degree. So there'll be some number d. Every single graph in the family, and every single vertex in those graphs will always have d neighbors. So d edges per vertex, d is fixed, and the number of vertices goes to infinity. So that's what happens in the family. The number of vertices should increase. And the idea of expanders and why they're called things like expanders, by the way, I should tell you, there are many names that variations of these go by and have gone by over time. Expanders, concentrators, something like that. I'm going to blur all those together and just call them expanders. And actually, my general philosophy of this talk is to be as imprecise as possible without committing any crimes. But if you want more precision, raise a hand or something. Okay, so expanders' idea is every set of vertices should have many neighbors. And what do we mean? Well, take a look at a set of vertices like this set of vertices S here. There are two vertices. And their neighbors are the other vertices that are attached to them by edges. Those are the other things that I put in green here. And also the nodes in S are neighbors of each other. They don't have to be, but these two are because they share an edge. Okay, we want there to be some constant bigger than 1, strictly bigger than 1. So for every set of most half the vertices, their number of neighbors is at least c times the number of nodes in that set. And that c is like I'll call the expansion constant. So here, this set of 2 nodes had 6 neighbors. We got a constant of 3. The constant is actually lower for this graph. We can take a look at another set of nodes. Like here's this set of 4 nodes that I drew. I had to reach around the graph to get them all. And they have in total among them 8 neighbors. So we see the constant for this set would be 2. And it gets a little bit lower when you look at bigger sets of vertices. And in general, that's a theme. Smaller sets of vertices generally have more expansion. Bigger sets of vertices have less. It's probably intuitive that should be the case. But often we make that formal and talk about the amount of expansion you have as a function of the set of the number of vertices. Though here I'm just caring about an expander has some constant c greater than 1. Okay, so the problem with expanders is that unless you are a very unusual human, graphs you can think of are not expanders. Right, so like the first thing people think about when they think about a graph, for a lot of people, is a grid graph. But this is not an expander, because if you take a look, at least it's not an expander family. At the set of, let's say, half the nodes on the left, you take a look at their neighbors, it's them plus this one little column on the right. So that adds on an extra root n neighbors. And when you divide by n, you see that the expansion constant as n goes to infinity, it's going to 1. So there is not a constant bigger than 1. Okay, you say, okay, let's fix things. We need some more neighbors. What about these graphs? Say, look at the complete graph. Every set of nodes has a lot of neighbors, but that's a problem because D grows with N. That's a complete graph on 10 vertices. And we need D to be constant independent of N. Say, OK, let's go for a hypercube. Yeah, that's a little better, but D is still growing with the number of vertices. So like most of the graphs people first think of are just not expanders. Unless you can think of a random graph. OK, it's debatable whether or not you can think of a random graph. You can say, I want to use a random graph, but can you understand a random graph or know what it is in your brain? Maybe not. At least you can't tell me who is the neighbor of what node. But let's say random graphs. We know that random graphs are usually expanders. And this was first proved, as I learned from Larry Guth's paper recently, by Kolmogorov and Barzin. I'd previously thought it was due to Pinsker. I will actually tell you why they were doing it a little bit later, because it's interesting. But first, let me just tell you roughly how the proof goes. So it's not hard, if you're used to combinatorial probability, to get some theorem like this. You first consider, I don't know, any set of vertices, like this set of vertices S. And then you say, OK, well, let's say I have a D-regular graph. They're going to have D edges leaving each of those vertices. And you say, well, what's the chance those edges only touch a few other vertices? The fewer other vertices you want those edges to land in, the lower this probability is. By the way, I know I haven't defined exactly what I mean by a D-regular graph. I'll give you a definition in a few slides in case there are a couple different definitions for a random graph. But OK, so you'd say, what's the probability of those vertices landing in a few other neighbors? You say, that's very small. OK, so the probability of low expansion is very small. And then you do a union bound. You sum up over all possible sets of vertices what that very small number was for that set of S. And you show it goes to 0. And then you show a random graph is a good expander with high probability. For those who think about such things, I want to mention 2 points. First, when you first try doing these analyses, or when you try teaching them, you think that the big sets are going to be the problem. Yeah, the big sets are the limiting factor, but actually the really small sets are the problem too. Because when you have a big set of vertices, you have an exponential number of things going on. It's very easy to say things happen, bad things happen with small probability. But when you have like 3 vertices, you don't have as much probability to work with. And that's actually where a lot of the difficulty comes into analyzing these things. So you have to take this sum, but you have to grade it by the size of the sets. And the one thing I'm uncomfortable with is I'm never sure if I'm getting this analysis right. I mean, I prove it's an expander. But to the best of my knowledge, I don't know if any random analyses of expansion are sharp for random graphs. So anyway, this is a question for probabilists in the audience. If someone knows a sharp analysis of the expansion of random graphs, please email me later. And if you don't, this is a good open problem for some students to figure out. Because I know when I'm doing union bounds, I always feel like I'm leaving something behind, or maybe I am and I don't know. OK, those were the 2 points I wanted to make about this. Oh, there was a third. Random graphs are actually usually amazing expanders, not just good expanders. So the most amazing expanders are what we call lossless expanders. This is when you have small sets where the expansion factor is about D. Like if every node has degree D, you can't expect expansion more than D. And these get there. If you take a look at sets of vertices that are like a small constant times, the number of vertices divided by the degree, they'll get expansion close to a factor of D. So that's awesome. I mention this because, unfortunately, this is the one thing Ramanujan graphs don't do. Well, OK, we don't know, but you can't get it from the Ramanujan properties. And I know I still haven't told you what that is. But it's motivated a lot of thinking. OK, so these are great, but you can't use them for everything. So we know that with high probability, a random graph is a great expander, but sometimes you can't afford high probability. For some of the applications I think about, you need to know it's an expander. You can't just know it's probably an expander. And probably an expander would be fine if we had a way we could check, but we don't have efficient algorithms for checking. At least up to some blur factor. So you can't really check if they're good enough in terms of like this sort of property. One of the main applications that excited a lot of people about expanders is that they can be used to de-randomize many randomized algorithms and used to make pseudorandom generators. OK, if you're going to use them to try to get rid of randomness, then you do not want a random construction. Probably, maybe a very small random construction, but you probably don't want one. So we want concrete ones. And also there are a lot of ways you can imagine that explicit expanders might be better than the random ones. We don't know. We don't know, as I said, exactly what is the expansion of these random graphs, or at least I don't know. Maybe someone does. So we needed explicit expanders. And Margulis in '73 gave us the first of these, which is sort of shockingly early in history. And it did have a constant c greater than 1. We didn't know what c was. And I think a lot of the reasoning about expanders was tricky until people realized the connection between expanders and eigenvalues. Okay, one great thing about eigenvalues, you can compute them. So we can check if we have the eigenvalues we think we do. Efficiently, you can compute them, even for really big graphs. So let me tell you about the eigenvalues. First, we need a matrix to take eigenvalues of, and we're going to use the adjacency matrix for the first part of this talk. So now I should get a show of hands. How many of you know the adjacency matrix of a graph? Okay, this is just about everybody, I think everybody. Just to say, if you don't, you make an n by n matrix, rows and columns labeled by the vertices, with ones between on-off diagonals where they're edges. Okay, if you have a d-regular graph, the largest eigenvalue will be d, and the others decreasing will be at least minus d. And we get a family of expanders if lambda 2 is bounded less than d. So by some fixed constant. So let's say it's an expander family if lambda is at most 1 minus epsilon times d. But the further lambda 2 is from d, the better the expander it is. And looking at this is sort of like discretizing results of Cheeger or building on works of Fiedler, who actually called this gap between lambda 2 and d the algebraic connectivity of a graph, but didn't relate it to expansion. The papers I know that first really did this in graphs were by Tanner and Alone and Millman, and they prove a result that looks sort of like this. Getting rid of the low order terms, which I can do when the set of vertices is small relative to n. The number of neighbors of a set of vertices will blow up the set of vertices by a factor of the square of d over lambda 2. So the smaller lambda 2 is, the greater your expansion factor. And so now we want to figure out how small can lambda 2 be. And this is established in bounds that, well, okay, there are a couple quantitative forms. Let me mention one of Alone and Bapana that we often cite. Tells us that lambda 2 basically is at least 2 root d minus 1. What do I mean by that? As n grows big, you can't get smaller than that by any constant. And there is actually some concrete bound. So we get 2 root d minus 1 minus this term I called little o of 1 as n goes to infinity. It's something like 1 over log n. So we know that as n gets bigger, you have to get closer and closer to 2 root d minus 1. So Lubatsky, Phillips, and Sarnak called graphs that achieve this bound of 2 root d minus 1 Ramanujan graphs. And then they produced them. And they produced more than that. So they produced infinite families of graphs where lambda 2 was at most 2 root d minus 1. Also, the smallest eigenvalue was bounded. So lambda n will be negative, but its absolute value is at most 2 root d minus 1. Oh, and I should mention Margulis made similar graphs, similar construction in the same year. Okay, so that is my very short summary of what Ramanujan graphs are. This leads people to wonder about, I'll tell you more properties of them. So first I should get back to the random graphs. So this led people to wonder, well, what about random graphs? How do they do on eigenvalues? Empirically, if you start generating random d-regular graphs, you find the eigenvalues often satisfy this bound. How often? Well, it depends on how big the experiments are you do, but you still find that happens. So people wonder, is it usually the case? We still don't know. Noga alone conjectured that you could get close. He conjectured that for sufficiently large n, or for all epsilon bigger than 0 for sufficiently large n, you would get lambda 2 at most 2 root d minus 1 plus epsilon. And Friedman proved this in 2008. by a paper that I will call like, it's those union bounds, but very, very complicated. A lot of worries go on when you look at small sets of vertices, about 100 pages of analysis. Like it can be checked, but I will admit I don't necessarily take intuition from it. Bordenov, who's made a lot of advances in random graph theory in the last few years, simplified this proof a bit. Just 4 years ago, it was 2019. But what's interesting, in the last week, there were some advances on this. So Chen, Garza Vargas, Trapp, and Van Handel put out a paper last week that my postdoc and I, Tim Kaniski, have been looking at, and we're convinced like it gives us a way to conceptually understand these proofs. So what do I mean? Like when I look at a proof with a lot of computations, with union bounds and a lot of binomial coefficients, I sort of worry whether or not there's a mistake somewhere, unless there is some obvious conceptual target that I am aiming towards. And I think this paper really has that. So I'll make that an advertisement for it. And then Huang, Mackenzie, and Yao, and I know I saw Mackenzie and Yao in the audience, put out a paper which gets amazingly sharp bounds on that epsilon, which we're going to hear about later today. So we're going to discover that that epsilon is now like 10 to the minus 2/3, which is as sharp as it can be up to some low order terms. So there's been a lot of advances here. By the way, we still don't know if these things are Ramanujan graphs with constant probability. I would really love to know that, but man, you know, the 10 to the minus 2/3 is good. It might not make a difference to anyone, but I'd like to know. Probably mathematically it makes a difference. Like you need to discover something to get below the 2 root t minus 1. Okay, I should mention there are variations on expanders. I glossed over them before, but like I was usually just taking an arbitrary graph. You can also make bipartite versions, and these are useful for a lot of applications. The bipartite ones are easier. So in Lubatsky, Phillips, and Sarnak's original paper, whether or not they were bipartite or not depended on whether or not primes were quadratic residue modulo on each other. I'll tell you where those come from in a moment. But let's say whenever you have a non-bipartite one, you can make a bipartite one by taking what's called a 2-lift of it. And sometimes we want unbalanced bipartite. So like every node on some side has degree C, and every node on the other side has degree D. These are 3 and 4 for some different C and D. There are also notions of what it means to be Ramanujan in this case, and people have built infinite families of Ramanujan graphs for special C and D. Those are useful as well. Okay, now that I put up the bipartite, I think I can give the cleanest explanation about how we generate a random graph. So to generate a regular random bipartite graph, let's say I want a 3 regular graph. Well, I'm going to put down all the vertices first. And I know that I want each of them to have 3 edges coming out of them. So let me draw the beginnings of those edges here for every single vertex. And now we just need to hook them up in between. And we'll do that by choosing a random matching from the left to the right of all the endpoints here to all the endpoints over here. So you choose a random matching, and that was a decent model of a random deregular bipartite graph. I mean, there are things that can go wrong. You know, I could wind up using a random matching, and I could like match these 2 edges to these 2, and then I get a double edge. Not the end of the world. We sort of call it an edge of weight 2. If I match 3 of them to 3, and by the way, it happens like about once per graph on average, or a constant number of times. If I match 3 of them to 3, then that's a problem, because then I'll just have 2 nodes that are only connected to each other and nothing else. But that's really unlikely. So that's how we generate them. So that's how I generated this graph. And then I checked that its eigenvalues were Ramanujan before I decided to draw it. And I'll admit the other ones, I generated about 50 Ramanujan graphs and pictures of them and took a look at the picture that was best that I could draw. Anyway, so this allows me to mention one other cool property of Ramanujan graphs and tells you where the lambda n comes in. I mean, why did they do lambda 2 and lambda n? I don't know if they did. I mean, lambda 2 we knew we wanted, lambda n, I don't know if that was just for kicks because they could, but it has meaning. So I want to like tell everyone why it's there. It's related to one of the pseudo-random properties of Ramanujan graphs. So to explain this property, I'll draw the picture with bipartite graphs. There's a version for the other case as well. So first, take a look at a random bipartite graph. Take a look at 2 arbitrary sets of nodes. I'm drawing them adjacent because it's easier to draw, so S and T. and take a look at the expected number of edges from S to T. Okay, in a random graph, you can figure out exactly what this is because it's just the sum over vertices in S and T, pairs of vertices, of the probability there's an edge between them. And if I take like some vertex in S, that one over there, the probability it goes to some specific edge in T, well, it's going to have D neighbors, their n vertices will be D over n. So the expected number of edges between any set of vertices will be the size of S times the size of T times D over n. Here's the cool thing. In a Ramanujan graph, that is approximately true for every set of vertices. So they act a lot like random graphs. So here's what I mean. For every set of vertices, S and T, here I drew them disjoint. There's a version for when they overlap as well. The number of edges in a graph G minus the expected number you would get if it were a random graph is at most lambda times the square root of the sizes of S, product of the sizes of S and T. So this means, again, every pair of sets of nodes in a Ramanujan graph has a number of edges like you would expect to get if you had a random graph. And when is this significant? Well, this is like what we find. This is the expectation. This is the deviation. It's really significant when the deviation is less than the expectation. And if you do a little math on that, you see it's significant when the ratio of lambda over D is less than the geometric mean of the sizes of S and T divided by n. So this tells you when lambda is small relative to D, this is particularly significant because it means the number of edges doesn't deviate much from the expectation. It also tells you that this is more meaningful when S and T are big. If S and T are too small, you don't get anything out of this, but that's what you'd expect. Like if S is a, one vertex, I can pick another vertex T that doesn't have a neighbor to it. If you give me a small set of nodes, I can find another small set of nodes that don't have any neighbors, but when you get big sets, this is significant. And actually, this is roughly equivalent to the previous theorem I gave you of Tanner. You can use, if you do a type version of this, you can use this to prove expansion. So these things are all related. This was, by the way, often called the expander mixing lemma. No offense in case Abhi is in the audience. I don't like that term for this. I'll call it the alone Sheng lemma, which is what you probably first saw it in, because I don't feel like this has anything to do with mixing. Okay. So now let me tell you more about the graphs that Botsky, Phillips, and Sarnak made. Okay, we've got an infinite family of D-regular graphs. Lambda 2 and lambda n are at most 2 root d minus 1. These graphs are explicit. You can say, you can give a very short description of exactly what the vertices are, exactly what the neighbors are, up to finding some primes. You say, okay, I need some primes. They're Cayley graphs. So that means that you have a finite group, and the vertices are the elements of the finite group. And then the edges are determined by a couple generators of the group. So you pick a couple generators of the group, let's say G1 through GD. You have an edge between vertices V and W if and only if W is equal to V times some generator. So to specify the graph, all you need to do is specify the group and specify the generators. Oh, I guess that generator set should be closed under inverses so that it's a undirected graph. You want VW to be an edge if and only if WV is an edge. Okay, so this is like an amazing family of graphs. They have all sorts of symmetries, of course, because there's a group underlying it, and the group acts on the graph. And that is incredibly useful for a lot of applications. And just to mention the group, although it's the projective special linear group of 2 by 2 matrices modulo Q, my students, when I did a test run, insisted I include an explanation of that, although this audience probably more of you know than no expanders. But let's just say, but it's simple is the point. You get 2 by 2 matrices, the entries modulo Q and determinant 1. And then you mod out by taking minus a matrix is the same as the matrix. So this you can compute with, which is incredibly important to us. And oh, right, I should say the Q should be a prime congruent to 1 mod 4, and the degree is P plus 1, where P is a prime congruent to 1 mod 4. And whether or not whether or not the graph is bipartite or not just depends on whether or not P is a quadratic residue modulo Q. Okay, so I've often described these Ramanujan graphs as the most amazing gift that pure mathematicians have given to theoretical computer scientists. Okay, some of my colleagues have said, well, like, what about Fourier analysis? And yeah, that's good too. But But that's not a gift. Okay, let me explain why this is a great gift. First, we would have never bought it for ourselves. Right? We wouldn't have known where to find it. I mean, why do they call them Ramanujan graphs? Because the way they prove this is because you exploit proofs of the Ramanujan conjecture, and this is like not a part of things that computer scientists usually learn in their education. So it's an amazing, and also they got the right bounds. We would have been happy with much less. Okay? So first of all, like I would have been happy to have lambda 2 at most some constant times d times square root of d. Almost every application I know, almost, would be fine with lambda 2 at most some constant times root d. But they got the exact right constant. And I just want to throw out that, and by the way, we would have also been happy with like a different exponent, like lambda 2 at most d to the 3/4. That would have been great too. But they didn't, they didn't bother to write a paper about that. They just went for the right bound. I want to add, like, to me, somehow, I don't know, intellectually, spiritually, this was important. So when you're a theoretical computer scientist, I mean, your business is still proving theorems. And a lot of these theorems look like, oh, something is polynomial time for some polynomial, or there is a constant such as something. And we don't always worry exactly about what those constants are. Okay? But if you really ever want to use something, suddenly you do worry about what those constants are. And they got us the right constant. This also gave me some hope in other points in my career that, hey, maybe we actually can find the right constant for some absurdly complicated looking thing. Having seen it done before really helped. The other thing I wanted to, maybe other impacts I should mention. So again, as I was like a student and thinking about computer science and math, and this was one of these things, or I think actually the first thing I thought were when I used in a paper, it's the first thing I used in a paper where I could not actually go back and check all of the details of everything else that I had used. Which was a little bit distressing to me at first, but I didn't know all of what goes into these proofs. And maybe with enough time I could have learned them, but I was also a little mercenary. I have to write other papers, got to learn other things. So I think this sort of brought some maturity to some parts of computer science, the idea that we were going to have to learn some other things we didn't know all the details of and use them. And of course, if you study what's happened in theoretical computer science, that's just the lay of the land these days, but it wasn't obvious it was going to be that way back in the late 80s. Okay, another reason these are great, I told you what the graphs are. It means, I told you what the graphs are. You can deal, if you know that P is a prime, you can deal with a very large prime P without too many bits. It means that, well, one way we describe this is if I write down a node, the name of a node using n bits, I just write down the entries of the matrix. Okay, if I have n nodes, I'm going to say I can compute the neighbors of that vertex and time polynomial and log n. But usually I'm dealing with very, very big graphs for a lot of applications, especially in cryptography and de-randomization. There, if the node I can deal with exponentially large graphs in the amount of time and compute that I have. So again, like if I have time order n, let's say, I can talk about a graph with 2 to the n vertices because it has this amazingly simple representation. And this was one of the reasons these graphs have been so useful to us. Okay, so I listed some early applications here. By the way, I define early as anything that happened before I was in grad school or maybe around that time. Your timeline may vary. Everything after that I call recent in my undergrads. Okay, what do you mean recent? But anyway, okay, so like when expander graphs were being used, people were looking at them for communication, like digital communication, for networking, for thinking about how do we communicate efficiently and how do we build routers. This is why sometimes you look at a big giant room of computers and there are wires all over the place. De-randomization, getting rid of randomness. Complexity theory, they started popping up in. And if you heard about the probabilistically checkable proofs or all sorts of results and hardness of approximation, expanders were sitting under there. They were getting used in cryptography and algorithm design. And I eventually came away with this message of when do I want an expander? Well, if I'm trying to prove a theorem and I've got something that's going to grow and I want something else to stay fixed, maybe an expander is the solution. Maybe that's how you're getting it. It pops up a lot in a lot of theorems where you wouldn't expect it. Okay, so I should also add, when I was in graduate school, it was clear there were so many applications. Like, we had to learn about this if we wanted to function. I mean, like, expanders were an example you had to have in mind. If you're going to prove a theorem about graphs, you should test it on a grid, test it on a complete graph, check it on a hypercube, try it on an expander too. But they solved a lot of problems. That was part of why I got into them, because like we had to learn about this. They were popped up all over the place. If you take a look at grad students today, what is the equivalent thing? Well, if they're in like theoretical computer science, these days they got to learn about stochastic differential equations. History's strange that way, or maybe large language models. But like it was like playing an analogous role back then. Okay, what I want to do in talking about applications, oh darn, the very top line is got killed by Zoom. Oh well. Let's see if I can make that go away. No, I can't. Okay, there we go. Okay, I want to tell you about the very first example I know of expander graphs being used for something. It comes from this paper, Probabilistic Logics in the Synthesis of Reliable Organisms from Unreliable Elements by John von Neumann. And here is this picture that appears in the paper. You see some edges here. There's some nodes that split 3 ways here. And there's some things on the right with arrows going to them, and they have 3 things coming to them. And in the middle, there is a random matching. That's what this U is, connecting the left and right. So I figured I'd tell you, why was von Neumann making random bipartite graphs? And by the way, I happen to conjecture that this is the first use of expanders, and I actually suspect, and I can give evidence, I'll give some, that all of the future applications actually intellectually stem from this. But I can't ask all of the people who were involved. Anyway, let's see. So here's what the problem von Neumann was concerned with. They're building circuits, and there are elements in these circuits, like vacuum tubes, that sometimes make errors. So what are we going to do about that? Well, he says, OK, let's imagine we have a bunch of, he didn't call them gates. I think they're called organs or something. But like we want to make a circuit with and or not gates, let's say, or anything that's enough to compute any Boolean function. And you have inputs to them, like on the left here, I have the zeros and ones. I'll use zeros for false and 1 for true, because T and F look pretty much the same when I write them. And we'll have 1 output. And he said, OK, what if these gates can be wrong with some probability, P, for each of them, at most? P will be small, like 1%. We'll do some amazing engineering, right, and get this down to 1%. Now can we make reliable circuits? You may laugh at things like that, but this is what quantum computing people are sweating over these days. Also, let me point out that he wanted to deal with big circuits. And as you get more and more gates, if you have some probability of errors, like, I don't know, there's some chance of probability P, that gate comes out wrong, it makes a 1, and then it corrupts that one. Well, you know, if there's a lot of gates and some fixed probability P of there being errors, then you're going to have some errors in the computation. And I got to also add P stays constant as n grows if you're lucky. Right? If you're lucky, putting more elements in your circuit doesn't make them less reliable. We know it isn't going to make them more reliable. Right? Yes.
I mean, is it natural to assume that these would be independent, or would you build up an increasing like cascade of effects?
Let's assume independence for now, because that's what von Neumann was doing. But yeah, the errors can, but yeah, conceivably some of the things that cause errors will not make them independent. You know, like, I don't know, a cockroach eating its way through a bunch of your wires or something probably has some locality to it. But that would be a different paper. OK, so here's a question. There's nothing you can do about the output. I mean, like, there is some chance that the output gate is just going to be wrong, let's say with probability at most P. But can we get the overall reliability close to P? And of course, von Neumann said yes. So let me give you the first idea. The first idea is, like, let's just make many copies of this circuit and feed the inputs into all of them. By the way, so von Neumann's model was errors in the gates, not errors in the wires. So I could replicate these. And then we need some sort of majority vote mechanism at the end. But this doesn't quite work. Because if you have number of gates growing and P being fixed, then probably all of these are wrong with some probability approach to a half, and the majority is going to be pretty messy. So there's no reason for this to work, but you just modify the idea a little bit. We're going to make many copies, but we're going to layer them on top of each other. Okay, so here is von Neumann's picture. Okay, and then we add an element he calls the restoring organ, which I will explain. It was that picture I showed you before. So we're going to make B copies. I call it B. B stands for bundle of every wire and every gate. And the wires are now arranged in these bundles, of B together. And they feed into the many, many copies of the AND gates, the many copies of NOT gates, and they come out in bundles. What we have, he calls it this restoring organ, this little purple rectangle that I drew there. I think of it as an amplifier that sort of boosts a signal. I'll tell you what it does in a moment, but first, maybe I'll do talk about what these represent. So if I have a bundle of wires, let's say here, and the majority of them are carrying the value of 1, then we think of that as a wire bundle representing the value 1. And if the majority of them are carrying the value 0, we think of them as representing the value 0. So the restoring organ amplifies agreement. The idea of this thing called the restoring organ is that, let's say here it is, I have something that's mostly zeros and 2 1s. Okay, you can see in my picture it comes out with only 1 1. What it has done is if the wires coming in mostly agree, then it increases agreement. So like it would take us from like 96% to 98%. And then the question, and that's going to turn out to be enough if you can guarantee that this thing increases agreement. And it's made out of wires and gates. You can make it out of and or not gates. He's going to make it out of majority gates. So here's how he makes that restoring organ. We have this random bipartite graph. And the inputs are those wires coming in, and then we have little majority gates. In this case, I only have 3 inputs. You need a little bit more than 3. You need a slightly larger constant. But whatever, you got some constant size majority, you can make that out of gates. And the idea is that if you have a lot of expansion in this graph, and you have just a few 1s as input, they're going to be distributed very, very evenly among the majority gates. So it's very unlikely, there could be a majority gate or a few that are seeing mostly 1s. But if there are very few 1s to begin with, very few of them are going to see that on the other end. So like here, I tried to draw pictures, even still visually confusing, of like where those 1s go. You can see there was one node near the top, which saw 2 1s coming in, so its majority was 1. But most of them distribute evenly if you have a lot of expansion. Certainly a random graph, which is what von Neumann was talking about. Okay, and then of course you do that, and then the majority gates can have errors. Okay, so we need to just say that if you have error probability at most p, then like this process, if the majority gates are correct, reduces errors. And then if it's very unlikely that more than 2 times p times b, or more than a 2p fraction of the majority gates have errors, you still don't have too much error. You add that in. And here's the overall picture, the way I like to think about it. Assume each bundle has at most, say, an 8p fraction of errors coming in. You feed it into the restoring organ. The restoring organ, if it works correctly, reduces the errors by a factor of 2. So you're down to like 4p fraction errors after the restoring organ. Well, except that some of the gates in the restoring organ could make errors. So that adds maybe another 2p. You're down to most 6p errors at the end of the restoring organ before you feed into the next gate. And then you feed into these gates like those AND gates. Okay, those can have errors. There are b of them there, but it's unlikely there's more than a 2p fraction of those in error. And when you're done, when I feed out from there, we say there are most another 8p fraction of errors there. There were most 8p fraction of errors in each bundle going in. That's what you need for induction. Okay, so that was von Neumann's idea. And von Neumann's analysis used random graphs. He skipped 1 or 2 details, corrected later by Dobrushin and Orchikov. And they show that you can do this with remarkably little redundancy. You need basically this bundle size to be the log of the number of gates in the circuit divided by the error probability. So that's pretty good. That's all you need. But this was done using random graphs. They didn't talk about expansion. If you analyze in terms of expansion, I promise you it's easier. If you analyze in terms of eigenvalues, it's even easier than that. So there was this really cool paper by Pippinger where he analyzed this in terms of lambda 2. And this is the entire proof. I thought about doing it, but I knew I'd run out of time. So let me just say, it's basically like if you have a set of nodes S that are in error, and you multiply it by the adjacency matrix of the graph, the probability, and you say the majority is only wrong if you have a bunch of big values here, that would result in a vector of too big a norm. And that's not going to happen because of eigenvalue bounds. And I guess the one thing, if you have really good vision, you might see there's number 8 to the 17 in here. That's because Pippinger was doing this with some lower quality expanders. With Ramanujan graphs, you can do better. OK, before I mention anything else, 2 other notes. So of course, these days you might wonder, well, what happened to this paper? Do we use it? As far as I can tell, no. We build our gates pretty reliably now. Until you talk to the people who are doing like nano manufacturing and things like that, and they're trying to make wires really, really, really small in circuits. And every few years, because as you make things smaller, they're more prone to errors. And you wonder, well, can you fix that? I wrote a paper about this. So every few years, someone calls me up from doing circuit design, asking like, can this help? And I'm like, well, von Neumann's solution, we don't actually want to use. And I'll tell you why in a moment. But it basically amounts to just making your wires a little thicker and your gates a little bigger. And they're like, oh, yeah, but we were trying to make them small, but then there are errors. And most solutions don't win that balance. Most solutions involve making things thicker, which, again, eliminates why things are unreliable. Other irony, so the reason that the expanders were originally constructed was not for an application. It was to address this question of, if I want to take an expander graph, can I actually wire it up as a network in 3-dimensional space? With wires, they have a physical diameter. And let's say the diameter of a wire is 1. And then they showed that if you want to take any graph and embed it in 3-dimensional space with wires of length 1, and they can't, of course, overlap, you need to put in nodes, you need a ball of radius like root n. And then they showed, and if it's an expander, you can't put it into any smaller radius ball. And as a matter of fact, with an expander, it'll cover almost all of the ball. The wires are for the whole thing. That's sort of why they're hard to draw good pictures of. It's why they're actually hard to stick into like VLSI or circuit design, because you start making your entire circuit wires instead of gates, which is not actually what you want to do. OK, I was going to talk about error correcting codes. Let me only just put up 1 slide about error correcting codes. 2, sorry. So I talked about computing with noise, but what about just like communicating with noise or storing data? This is one of the first applications of expander graphs. So Gallagher, in this paper called Low Density Parity Check Code, suggested what we do to figure out what messages we might send or not is we make a graph. It's a random bipartite graph, more nodes on the left. We associate bits with nodes on the left. Nodes on the right impose parity constraints. So they're not computing anything. They're just saying every node on the right here says the nodes on the left that are neighbors of it have to have parity 0. So like that node says those 4 nodes on the left of it have to have parity 0. By the way, I didn't check if the rest of this satisfies all those constraints. This turned out to be very useful for communicating. But I want to point out that Gallagher, again, doesn't talk about expansion, didn't know about that yet. But Gallagher's advisor was Peter Elias. 2 years before Gallagher wrote this, it was his thesis, Peter had written a paper about von Neumann's construction and trying to integrate it with error correcting codes. So I have a suspicion that Gallagher got the random bipartite graph from Elias, who got it from looking at von Neumann's paper, or at least Peter Elias had made Gallagher look at all that at some point. And now, do I know that Gallagher is the source of expanders? I don't know. But I do know that Gallagher's paper, while these codes are incredibly useful today, were ignored by most of the world for a good 40 years. 30 years. Except by some Russian authors like Dobrushin and Pinsker, who were analyzing Gallagher's codes. So I suspect that that's the connection. But that's all I'll say about error correcting codes? Unfortunately, unless anyone pings me later. Okay. Let me tell you just a little bit, I got to say something about my own work, about a completely different sort of application, partially to get us out of bits. I've been talking about 0, 1. I think it's time to talk about some real numbers. This is some applications where actually getting like the right bounds on eigenvalues matter. So let's consider an algorithmic application. Let's consider a whole different problem of solving systems of linear equations over the reals. And the sort of systems I want to solve are defined in terms of Laplacian matrices, which for now, think of as you take the adjacency matrix, take the diagonal matrix of degrees, like d times the identity, subtract off the adjacency matrix, that's the Laplacian matrix. From that formula, it's not obvious you'd want to solve equations in them. If I write the corresponding quadratic form, x transpose Laplacian x, then it might be more obvious, because it's the sum over edges of the square of x at vertex u minus x at vertex v. Okay, so we often want to solve systems of linear equations in these. And in general, when you want to solve systems of linear equations, we usually do it by Gaussian elimination. At least that's the first thing we learn. So if I want to solve like mx equals b, I write m as L times u. Oh yeah, I'm going to use a script L for the Laplacian, because for now my regular font L is a lower triangular matrix. So when you do elimination, you take a matrix, you write it as a product of a lower triangular matrix times an upper triangular matrix. And once you've done that, you can solve systems of equations in M. Because M inverse you can write as U inverse times L inverse, and because they're triangular, you can multiply by U inverse and L inverse in time proportional to the number of non-zeros in L and U. Okay, that's Gaussian elimination. When you want to do it for Laplacians, we know, this is in a paper of myself with King, Li, Peng, and Sachdeva, that there exists an approximate LU factorization where L and U are very sparse. In particular, for an n by n matrix, we can make lower triangular and upper triangular matrices L and U where they have at most some constant times n entries. And the product approximates L. I'll define approximation in the next slide. But let me just tell you now, it's enough for solving systems of linear equations once you have this in time order n. But if you look at this proof, this is like an appendix in this paper that, the theorem is stated too, but probably not many people read, because we don't have an efficient algorithm to go with it. It's an existence result. There's like a quadratic time algorithm. But I wanted to mention, because if you take a look at what's happening inside the paper, we need to replace a bunch of complete graphs with very nearly Ramanujan graphs. And this is one of the places where I know that we need things where the eigenvalues are most to constant times root d. We also need them of every single size. And let's just say there's sort of a folklore of how to take Ramanujan graphs and hack them so you can get any number of vertices that you want if you're willing to sacrifice a little bit on the degree. And this is one of those papers that has that in it. By the way, I should just add, if you're willing to just be a little bit worse than a const times n, like c times n times log n, yeah, then we have efficient algorithms. But when we get down to this point, at least I don't think we know how to do it yet. Okay, I should tell you what an approximation of a graph is, because this is one of the ways that I really think about Ramanujan graphs and expanders. So I will say that a graph G is an epsilon approximation of a graph H. When I take a look at their Laplacians, I take a look at the corresponding quadratic forms, they're always approximately equal to each other. That is, for any vector x you take, like I take the quadratic form of x in the matrix L, it's at most 1 plus epsilon times the value you get in the quadratic form for H, and vice versa. So this is a notion of approximation that turns out to be very useful for doing numerical linear algebra. And Xianghua Tang and I defined it. You can ask, why did we think such a thing would exist? Well, in part because expander graphs are approximations of the complete graph under this definition. And we figured if I could take the complete graph, maybe I can find good approximations. And we want approximations that are very sparse. So like Ramanujan graphs are 2 over root d approximations of the complete graph under this definition. And they're d-regular. So the densest graph you can make, a complete graph, can be approximated by a very sparse one very well. And this, again, knowing this existed, later inspired Batson, Srivastava, and I to come up with, try to figure out like how well can we approximate an arbitrary graph by a sparse graph? Can we do as well as we do for the complete graph? And well, our paper was called Twice Ramanujan Sparsifiers, which says that for every graph G can be weighted. You can put weights in the quadratic form. There's a weighted graph H with the most dn edges that approximates G as well as the Ramanujan graphs approximate the complete graph. And these are called twice Ramanujan because they have a few too many edges. So dn edges is average degree 2D, whereas Ramanujan graphs are average degree D. But so we know that there is something like this. For every single graph, you can approximate it by a sparse one. And then someone basically asked, Gil Kalai, but if we apply these sparsifiers to the complete graph, what do we get? And the answer is a very strange thing. If I apply this technology to the complete graph, I don't get back a Ramanujan graph. As a matter of fact, I get back a graph with weights on the edges, which seems weird. You would think all the edges should come back weight 1 or something like that, or weight n over d. But no, we get weighted graphs. So we're wondering, can we get rid of those weights? And if you try to answer that question and figure out what it means when you look at our proof, so our proof actually doesn't have anything to do with graphs. Very quickly translates to a statement in linear algebra. And if you think maybe you don't need the weights when you're making a complete graph and approximating it, then that linear algebra statement turns out to be this conjecture of Nick Weaver. And that conjecture was equivalent to the Caddison-Singer problem. And we thought, oh yeah, okay, well, we don't need those weights, right? Because Ramanujan graphs exist, and they approximate the complete graph this well. So we should prove that. So here is a very brief history of one of the highlights of my career. First, we tried to prove Weaver's conjecture. And that was great. It was fun. But eventually, we got sort of hurt after a few years of banging our head against the wall. We decided, let's see if we can do something better. Let's take that intuition we had that we didn't need weights to approximate the complete graph. And when we take that intuition, we said, OK, maybe we can now prove there exist Ramanujan graphs that we didn't know before. Because previously, the Ramanujan graphs we had depended on these primes P and Q. And people were wondering, does it have to do with number theory? Or just, do they always exist? So we proved that there exist, at least the bipartite ones, the easy ones, Ramanujan graphs of every degree, at least 3, using some of the technology we've been developing for Weaver's conjecture. And it was a good thing we wrote that paper, because as we were writing it, we learned a little more, we understood our techniques better. That let us go back and prove Weaver's conjecture and solve the Caddison-Singer problem. And then that also, afterwards, we were able to prove there exist bipartite Ramanujan graphs of every number of vertices in every degree. By the way, this is very much an existence proof. You cannot, well, OK. The first one is very much an existence proof. The second one, we thought it was an existence proof, but Michael Cohen actually figured out a way to make it algorithmic. So you can turn that into an algorithm for producing a Ramanujan graph, only the bipartite ones, and still not with a nice compact description. So your algorithm takes something like polynomial in the number of vertices, whereas the explicit Lubotsky-Phillips-Sarnak graphs, it's like logarithmic in the number of vertices to describe it. So there's a lot we still don't know here. By the way, we still don't know if there exist Ramanujan graphs of every number of vertices and degree. I mean, we think there do. We only know it from the bipartite case, which is what we get out here. We don't know about it in the non-bipartite case. And random graphs might be doing this. We don't know that either. I would love to know. OK, so I've told you about some of the impacts of expanders and Ramanujans. In Ramanujan graphs, why don't I just mention some of the most recent things that have happened that have been exciting in the last few years. Ramanujan complexes and high-dimensional expanders have generalized these in ways that, admittedly, I thought, OK, I'll admit, it wasn't clear to me this was going to be useful, but totally was. They brought us recently amazing advances, things called locally testable codes. Catch me over T if you want to hear me rave about those. And quantum low density parity check codes. And the quantum world is so much harder because you can't just make things thicker. If you make things thicker or bigger, you lose the whole quantum things. OK, and there have been many, many more applications. I don't know what the others will be, but I'm sure we'll hear about some more this week. So thank you, Peter.
Thank you. Thank you for an amazing talk. We have time for questions and comments. In fact, we have just 4 talks a day, so please.
Okay. Wonderful talk. I can just shout, right?
Yes, yes, yes. Especially.
Yeah. I have a loud voice. Yeah, wonderful talk. Maybe you know, maybe you don't know, but I used to give a lecture about these graphs of ours and say that nobody will ever make it without number theory. So you have to eat humble pie when you did it. But I'm glad you highlighted the fact that you're only making bipartite so far. So I continue to hope that you don't make the jump. Anyway, I think it's wonderful to see how they use.
Yeah, I mean, and I'm sure many of you will know other applications, right? And they appear in group theory and in algorithms, all sorts of places you wouldn't, geometry, all sorts of places you just might not expect them to get used. They get used. And yes, as you said, my explicit constructions have nothing to do with number theory to the best of my knowledge. I mean, sorry, they're not explicit. Our existence proofs. We have no idea what the graphs are that you get out.
Further comment I have, that does connect you with another story. And it's the Li-Yang theorem, which is a theorem which you use indirectly through Helm and Lie.
Yes.
And that's a theorem which ensures that certain polynomials have all their zeros on a circle. And in the proof, of course, that these graphs are Ramanujan, which uses eventually Bayes' proof of the Riemann apartment for total finite fields. There's also a theorem about polynomial having all the zeros on the circle. That's common.
I didn't know.
And that's being used in, so Li-Yang is replacing Riemann.
That's interesting. Cool. Thank you. Great conjecture. Or not great connection, I mean, yeah.
So does your method imply something about the girth conjecture?
Oh, about the girth, no. So, oh yeah, so some of you know, and for those who don't, one of the cool things about the Ramanujan graphs they built is they have no short cycles, and the lower bound on the length of the cycle is better than anything else we know, and better than you can get out of random graphs. And yes, when we were working on trying to build expanders, we were wondering, we were trying to build the Ramanujan graphs, is there a way we could prove lower bounds on the girth? And no, we could not find a way of doing that. And I don't know how to incorporate that into the technology we built. But I mean, let's put it this way. It's not crazy that it would be possible. I just don't know how to fit that into the tools we had at the time. But people have improved on these tools since then. So, I mean, there are a lot of extensions of these results that I had, and some of them might help. Yeah.
The von Neumann's duplication of the gates. You mentioned that the number of the degree would have to be a little bit bigger than 3, but is it still a constant?
Oh, yes, yes. The degree is still a constant. I don't know what the best degree is right now, but I think once you plugged in Ramanujan graphs, it turned out to be somewhere between 10 and 20. So it wasn't so bad. Oh, yeah.
Lower bound of alone, saying, I guess if you have a D-regular graph, the lower bound is like 2.
Right.
But if you kind of maybe relax regularity a bit, can you do better?
Ooh. So if you know, sorry, let me be careful when I say that. When I say, so it's a good question. The question was, I gave this lower bound, and you can ask, especially once I threw up those sparsifiers, you can ask, can you approximate the complete graph better by like even a weighted graph with a lower number of edges? And as far as we know, no. And now I have to remember the difference between what are theorems that people proved and what are homeworks I've assigned, and I don't completely remember, but I think the answer is pretty safely no. And I know there's some theorems about this. I also remember there are 1 or 2 funny cases that I don't think were covered by them, but probably can be with a little bit of work. So yeah, we can't do better. Oh, yeah.
Is it possible to say something about why it is hard to prove that an explicit graph is Ramanujan?
Oh, sorry. If you give me sorry, it depends what you mean. So if you give me an explicit graph, if I can actually write it down and write down all the vertices, then it's easy to check. We compute the eigenvalues. But if it's implicit and you just give me, well, first of all, the question is, how do you give me a description of an implicit graph? There aren't actually that many ways to like describe a graph on 2 to the n vertices of n bits. Cayley graphs are some of the best. And then the other ways are you can give me descriptions of different, there are other products and operations you can apply and lifts and things to make graphs. But okay, so if you want Cayley graphs, then you need to look at the representations, usually to get at the eigenvalues. And unfortunately for all these graphs, the representations tend to have pretty high dimension, which actually makes figuring out what your eigenvalues are and computing them a little trickier. Unless you, oh, fortunately, okay, sure, fortunately. Depends on what you're trying to do with it that day, yes. Yeah, so, and yeah, and when you have, there are other constructions of graphs that are pretty cool, like there are these constructions of lossless expanders, but actually figuring out what their eigenvalues are hard. We can prove different things about them, but the actual constructions, it's just not always easy to trace out how the eigenvalues are going to behave, which makes sense because, you know, you're trying to get something that is right at the limit of what is possible. So it's not surprising that if you have a somewhat more complicated construction, it's easy for there to be slack in your analysis, and then it's hard. Oh, yes.
You mentioned something about Ramanujan graphs being sparse graphs, which can approximate dense graphs in some sense.
Yes.
Well, just remind me, was that sense of approximation with the quadratic form?
Yes. So the notion of approximation, the Ramanujan graphs approximate dense graphs in the quadratic form. And there's one thing I forgot to do when I said that, which might have confused someone, which is what I'll call conservation of mass. If I need to have the same sort of number of edges, it's just that in Ramanujan graphs, they're all on top of each other. So you take the Ramanujan graph and replace every edge with an edge of weight n over d. And then you're approximating the complete graph on n vertices.
Ramanujan graphs is the only example we know of sparse graphs which can approximate dense graphs in a sense.
Yeah, well, okay, so they're the only, Ramanujan graphs are the only ones that approximate the complete graph this well. But for arbitrary graphs, then my work with Batson and Srivastava tells us there are sparse graphs that approximate them well. Just the number of edges is about a factor of 2 more than we get from Ramanujan, and I don't know if that factor of 2 can be saved or not. It's slightly less than 2, but yeah. We're like, could it be 1.5? I think that's still open, and I would love to know.
Are there examples of bipartite graphs where the expansion constant coming off of the red, if you start with a red collection of vertices, it differs from what you get by starting with the other blue set of vertices like that? I don't know this question.
You're saying, so could the expansion constant be different from side to side? To some degree, I haven't really thought about it. I mean, okay, you know, if it's unbalanced in the number of nodes on either side, yes. But I guess the answer is probably. You know, we could probably cook up some examples where it's not as, where it's more favorable one way than the other. But I hadn't, yeah, I'm pretty sure I can cook one up, but I don't know how extreme the difference can be.
Any other questions? If not, let's